I'll make it back.
Okay, so let's chit chat about the two labs, okay? And I promise you, there's gonna be questions like this on the test tomorrow, okay? So let's make sure everybody's cool.
Okay.
So, if you look at that very first thing, so let's start with the one that has like the inclined plane, not the magnet lab, the inclined plane one, which is the yellow one, okay? And I emphasize this again, these are two completely separate labs. I do not want anything crossing over on the diagrams, okay? Treat these as two completely separate labs, okay? So, if you look at what happened on the first one, you took an inclined plane and you had it sitting here and you put the block on it and you began to lift it up. Now, something as innocuous as this actually holds a lot of important information. So, this is a situation where I have forces acting on the system. But what's the acceleration? Do not make this difficult. What's the acceleration of the stopper?
9.8. Wait, what? What are we talking about?
Zero.
Oh, it's wait.
What's the acceleration of the stopper?
Zero.
Right here.
Zero.
Okay, yeah.
Obvious. Yeah,
It's not accelerating.
I did not know what we were talking about, to be honest. I thought we were talking
Are there
about the lab.
forces acting on the stopper?
No.
Yes.
I mean, yes.
There's all these forces that.
Well, you don't get the answer.
I know the answer.
No, you don't get the answer.
Okay. I don't want to answer anymore.
Are there forces acting on the stopper?
Yes.
Yes. But is the stopper accelerating?
No.
So therefore, all the forces add up to
Zero.
So if you look at the forces acting on the stopper, okay, what's one of them?
Force parallel.
Gravity. Okay. What's another one? Force normal. And that's going to act at a right angle to the surface.
Yes.
Okay?
Agreed. I'm sorry.
It's okay.
What are you eating?
It's just kind of random.
Oh,
That's all. Okay. So there's two. What's another one?
Force parallel.
Force parallel, which always acts which direction? Down. And oddly enough, parallel with
Oh, it's
it.
always down.
Okay? Hence the
Store that in my
term
brain.
force parallel.
Always
Okay?
down.
Now, Dime, if those were the only three forces, would the object accelerate?
Yeah, because it's just going down.
Yeah, okay? There's nothing to oppose that force parallel. So if those are the only forces acting on the system, the object would be accelerating down the inclined plane. Obviously, it's not. So what does that mean? Something has to be balancing out that force parallel, which in this case is going to be what? Friction. Okay?
Let's go.
So what that means is that that force friction has to be greater than your force parallel. So this is a battleground between the two mafias. Okay? You have the gravity mafia trying to pull it down, and you have the frictional mafia holding it in place. Okay? Forces are acting on the system. It's just not accelerating. Okay? Now, if I lift it high enough, what's going to happen? And it's going to begin to slide, right? So at that point that it just begins to slide, we're assuming that the force parallel, the gravity mafia, is equal to the frictional mafia acting up. Now, if I go really steep like this and let go of it, which one's a lot bigger then? Yeah, the gravity mafia is much bigger than the frictional mafia. Okay? So, we took advantage of this. We said that if what we did is we set the force parallel equal to the force friction, and we ended up with tangent theta. Okay? That only works for static friction. It does not work for kinetic friction. Okay? It's the only time that works. So, did that part easy, lift it up, began to slide, boom, there you go. Now, The slightly more complicated one is where you set it at 30 degrees. Okay? And again, you have your gravity acting down, you have your force parallel, you have your force applied, you have your force normal. Now, what else is there? There's friction. Now, here's how you know that there's force friction. Okay? Here's how you know that there's a frictional force. So let's just say that your block weighs 3.80 newtons. Okay, so that's the gravitational pull. You lifted it up, boom, you got the reading on the scale, 3.80 newtons. Okay? So, because you're at a 30-degree angle, your force parallel is half of that, because the sine of 30 is 0.5. You take sine of 30 times 3.8, you would get 1.90 newtons. So, that means that that force parallel is negative 1.90 newtons. So, at a minimum, to pull this thing up the hill, you have to apply 1.90 newtons of force. At a minimum, okay? Because you have to overcome the gravity mafia. So if this is a perfectly frictionless surface, your force parallel acting down would equal your applied force going up, if it was a perfectly frictionless surface. So anything above and beyond 1.90 newtons is used to overcome friction, okay? So let's say that your applied force was, let's say 2.20 newtons, just to make up a number. Okay, so let's say that's your applied force. You measured it, that's how much force it took to pull it up. So what that means is that force friction going down the hill plus this force parallel have to add up to 2.2. So here's the first thing I'm going to check when I get to this lap and I get to this part of it. Here's what should happen, is that force applied should equal the sum of your force friction and your force parallel. So that's the first thing that you want to look. Look at that vector diagram. Does that applied force going up the hill equal the sum of your force friction and your force parallel going down the hill? If it does, you're good. Okay? If it doesn't, something's gone horribly wrong. And if you're not sure, give your paper to a study buddy and go, hey, does my applied force equal the sum of those two values? Okay? If they look at it and go, not even close, something's wrong.
Not even
Okay?
close.
So, your applied force going up the hill has to equal the sum of the two values going down the hill, which is going to be your force parallel and your force friction. Everybody cool with that? Now, you're going to calculate your force normal. So there's a couple of things I'm going to look for. Number one, can I see all your calculations? Because they'll tell you up at the top, wow, show all your calculations. You should have one vector diagram for this lab that looks like this, okay? You should have a total of 5 forces, okay? Total of 5, all right? The gravitational force, your force normal, your force applied, your force parallel, and your force friction. Okay, so those should be the 5 values you have drawn. This should be drawn at a 30-degree angle. Okay? Cool with that? We're good. Show me the scale. Did you let 1 centimeter equal a newton? Did you let 2 centimeters equal a newton? Okay? Show me what that scale is. So somebody should be able to take your paper, look at that diagram, know exactly what your scale is, know exactly what the forces are, and the value of those forces. Okay? Any questions on that part of the lab? Okay. Now, let's talk about the problems down below. So what's happening here is just a more of a mathematical way of viewing these problems. So what you're saying on these is that there's friction. So all you have to do on this first problem is find your force parallel, find your force friction, add those together, boom, there's your applied force. Now, here's what I've noticed that where this is getting a little glitchy, okay, which is not a highly technical term, but it's a little glitchy. That force friction is mu times force normal. Okay, so this is where you're going to have to do a substitution. So your force normal, if you look on your equation sheet, okay, your force normal is Fg cosine theta. Okay, and then the next question is, oh, how do we calculate Fg? Oh, so that's mu mg cosine theta. So if you want to find your force friction just in one calculation, take mu times your mass times g times the cosine of the angle. All you have to do is just plug in the numbers. Read through the problem. I've given you mu, I've given you the mass, you know what g is. Assuming that you're in radian, not in radian mode, and you're in degree mode, you should be able to get that force friction in one step, okay? Just plug in all the numbers. Mu mg cosine theta, okay? Now, because you're pulling it up the hill, Mason, which direction is my friction going to act? Down the hill, okay? So you're going to have some applied force going up the hill, and your frictional force is going to act down the hill. Because you're pulling it up the hill, Maggie, you're pulling it up the hill, what other force is acting down the hill? Parallel. So that applied force should equal the sum of your force parallel and your force friction. So if all goes well on that one, that force on number one should be around the legal drinking age, okay? Not what you think it is when mom and dad are out of town, okay? Something around the legal drinking age. Huh? The legal drinking age.
I thought you were talking about this 0.38. I was like,
Okay? All right. Now, number two is the exact same concept as number one. You need to find your force parallel, you find your force friction. You're going to get a force on number two that would make a pretty decent GPA. Okay? Not stellar, but not bad. Okay? So the total force that you need on number two would make a decent GPA. Okay? I didn't say stellar,
The
decent.
force, not
Okay?
the mass.
On a non-weighted scale. How
The
about
force,
that?
not the. He's different.
Okay? On a non-weighted GPA scale.
Yeah, we thought we were talking about the mass.
No, that's just the force. Just the force.
Yeah, we were confused for a
Okay.
second.
Yeah, 3.7.
So
Yeah, but imagine
what's happening here is that you need a certain amount of force to pull this thing up at a constant velocity. Okay? So you can either grab it and pull it, or you can let gravity do the work. So what you've got to figure out is how much mass you have to put on the end of that string to create that much force. Okay? Now, notice we're not accelerating. Moving at a constant velocity. So let's say that you needed, I don't know, just make up a number. Let's say that you needed 4 newtons of force out there on the end. So you needed to pull this thing down with a force of 4 newtons. Okay? Well, let's make it easier. Let's say you needed 9.8 newtons of force. If you needed 9.8 newtons of force, what mass would you put on the end of the string? 1 kilogram, because 1 kilogram times 9.8 gets you 9.8 newtons, right? So basically what you did without thinking about it, you took the force and you divided it by 9.8 meters per second squared to find the mass. So if you need 4 newtons of force, assuming that you're on Earth, take the 4 newtons, divide that by g, there's the mass that you're going to get. So that answer on number 2, okay, that mass should be between 0.2 and 0.4 kilograms. Okay, so that's the range of that mass. Now, when you do number 3, you don't have to recalculate anything to do number 3. You're going to use the exact same numbers that you used on number 2. But what's the difference between number 2 and number 3? It's the only difference. Friction. Friction in this case is acting which way? On number 3? Up the hill. Because on number 3, you're letting this thing go down the hill. Okay? So you're letting it go down the hill, so friction is acting up the hill. So on number 2 and number 1, you're pushing it up the hill, friction is acting down the hill. On number 3, it's going down the hill, so friction is acting up the hill. So your answer to number 3, okay, is going to be less than your answer to number 3 is going to be less. Go ahead. Huh? Okay. Wow. Okay. So your answer to number 3, in terms of mass, okay, listen to me, in terms of mass, should be between 0.1 and 0.3 kilograms.
Agreed.
Agreed?
Yeah.
Okay. Everybody cool with that one?
Yes, sir.
Got it? Good?
Actually,
It's always
okay,
you.
I was like, when I was thinking about this, I just came to my mind when we were talking about the vectors. Can I just attach my force friction vector like onto that line down there? Or do I need to have it off the tip to
I
tail?
don't care where you
Does it have to
draw
be like
it.
tip
You
to
can draw it
tail?
like side by side with the force parallel, and you can put it at the end like that. I don't care.
Oh, okay,
Just
so,
as long as I see where it is and it's clearly labeled.
okay,
Got it?
sounds good.
Good with that one? Good.
Yes.
I was thinking, can I find force friction at the, like,
Drop the pencil.
Okay. That's how much force it took to pull it up. That's your force parallel acting down.
just,
So the difference between those two
This is wrong.
is used to
He looks
overcome
like a
friction.
bird.
okay, thank you.
So anything above and beyond your force parallel
Your mommy said
is overcoming friction. Does that make sense? Okay? Because at a minimum, it would be your
Are you
force
gonna go to
parallel.
Walmart?
Okay?
Yeah.
Okay. Are we good? Okay, let's talk about the magnet lab. I promise you, there's going to be a question involving this magnet. Okay? I promise you it's going to happen. You mark my words. Okay? It's going to happen.
Test.
So, here's the cool thing about that magnet. Is that it always acts, listen to me, that magnet, in case you haven't figured out, always acts to oppose the motion. Okay? That magnet will never make something speed up. Okay? Without spending an entire day on electromagnetic theory, on why it works. The short version is that Mother Nature hates change. So this is why it only drags when you're moving it. Okay? Because what happens is that you have a magnetic field. Mother Nature senses a change in the magnetic field, and it creates a magnetic field in the metal that opposes the change in the magnetic field, and that's why it's a braking force. So listen to me. Listen to me. Listen to me. I'm going to tell you this on the test tomorrow. If that smells, so help me. If that smells like fruity stuff,
No, it's not. It's stress relief.
Eucalyptus and spearmint.
Eucalyptus.
Stress, okay.
It works. After I did horrible on your test, it works.
It's mine.
You
You ate it the other day.
I
You're
don't
like,
care.
ew.
I'll live with it. I need to release some stress.
Yes.
Okay. Oh, I just feel better already. Okay. Okay. Right now I feel like low coefficient of friction. Here we go. Okay. So. Wow. Woo, that smells. All right. So speaking of opposing forces, so here's the basic idea. The first thing that you did is you set that cart on an inclined plane, right? We're assuming that it's frictionless. So it's the only force available to accelerate the cart,
Parallel.
force parallel. And that's always going to act which way?
Down.
Down. Okay? Now, when you get this problem on the test tomorrow, Okay, and I promise you, this problem is going to be on the test. You mark my words, okay? And I'm going to say, here's this little magnet, okay?
Okay.
And if the cart rolls down the hill, the force of the magnet is going to act up the hill. If the cart is being pulled up the hill, the force of the magnet is going to act down the hill. So listen to me. Listen to me. And I'm going to tell you this in the problem. The force from the magnet is going to create an opposing force, okay? Which means if the cart goes down, the magnet goes up. The cart goes up, the force from the magnet goes down, okay? No exception. So the magnet is acting like a frictional force. It's always going to go in the opposite direction, okay? Got this. So now we have the magnet mafia, okay? So the magnet mafia always opposes the motion of the cart. So we have the gravity mafia, the frictional mafia, now we have the magnet mafia. Okay, so now we got all three involved in this story. Okay. So, you let this thing roll down, you calculated a theoretical acceleration based upon that angle, okay? You took your force parallel, hopefully, and you divided that by the mass of the cart to get an acceleration, okay? Because we're assuming that's the only force in town. Hopefully you got some numeric values, you got your acceleration. You use 2d over t squared to get an experimental acceleration, okay? Now, here's the deal. Then you put the magnet in it. So what happened to the times once you put the magnet in the cart? It increased, which means what? Yes, it did not accelerate as quickly. So what that means is that the gravity mafia is trying to drag it down. The magnet mafia is pushing it up. Okay? So the difference between those two is the value. So what you can do is you can calculate your net force. No, seriously. Okay. I'm going to have to reevaluate these numbers. So here's what you're going to do. You know your force parallel, that's acting down the inclined plane. You figured out what the net force is. So here's the basic idea, is that net force is going to equal your force parallel plus the force from the magnet mafia. Okay? Now, remember, it is only your net force, and it is only your net force that equals mass times acceleration. Now, think this through. What's going to be the sign of your net force? Positive or negative? Negative. How do you know? It's going down the hill. We define down as being negative. Okay? So make sure that your answer to number 6 is a negative value. Okay? It has to be. Okay? Because you're accelerating down the hill, right? Now, on number 7, you're going to try and find the opposing force from the magnet mafia. That is acting in the opposite direction. So what sign does your answer to number 7 have to be? Positive. So you know your answer to number 6 is a negative value. Your answer to number 7 has to be a positive value. Okay?
7 is the time.
No, on the back.
On the back.
This is on the back side.
Oh, I was
Yeah,
like,
I'm on the back side. I'm sorry. Yeah, I'm sorry.
On the back.
I'm over on the back side. I'm big picture at this point.
To you.
Yeah. So, yeah. So this is on the back side. I'm sorry, I didn't make that transition. So your answer to number 6 is going to be negative value, because that's going to be your net force. And then number 7 is your opposing force, which is going to be acting up the inclined plane. So basically, that force from the magnet is typically a very small number. Usually, this is an ish, it's usually around 0.1. Okay? That's a huge ish, okay? But it's generally around 0.1. If you have a force from the magnet of like 12, you have done something horribly wrong. Okay? That's generally where that's going to be. Now, on the diagram on number 8, which again is not going to be on the same page as the first diagram with the inclined plane. Okay? This is not on the same page. So come in here, and typically this angle is going to be pretty small, like around 1.7 degrees, something like that. Okay? So that's going to be pretty shallow. Okay? It's going to be a pretty shallow angle. Not flat, but it's not bad. So you can just draw your cart and go, here this is. So you're going to have your FG, your force normal, your force parallel, and your force from the magnet mafia. Now, because these numbers are so vastly different, you want to use two different scales. Okay? Okay? Mainly because the gravitational force is really, really big. So in that situation, you might let like 2 centimeters equal a Newton, okay, or something like that. And then have a different scale for what's happening on the parallel. So make sure somewhere that I can clearly see which scale is which, okay? So you could say maybe your force parallel, magnet, whatever you're going to let, 2 centimeters equal a Newton, whatever you're going to do. And then your force G and your force normal, what that scale is. Okay? And again, if you're not sure if you've done that, give your paper to somebody else and go, hey, can you figure out the scale that I've used? And if you can, hey, you're probably okay. If they're looking at this going, I don't see a scale at all, that's bad. Okay? Any questions on that one? Maggie?
I have a question on the other graph.
Which other graph?
From the yellow page.
Yeah?
So since force parallel and force friction are acting the same way, we just like the vectors like line it up.
Yeah, you can
We can just like stack them.
You can do this one of two ways. You can either draw them as two separate things, okay? Or you can just draw them one like this and then put the other one on the end of that.
Does the length include, like, as when you measure it, do you, for each vector, like when you put them like on top of each other, is it still from the middle?
No, it's from the end of that.
I need to fix that then.
Okay, they're two individual.
So I have to do like tip to tail on that kind of thing?
Yeah,
Oh,
but
okay.
you're making this difficult.
No, because I just like, I measured like the whole force parallel and then I just measured on top of my vector like the amount from the, you know?
No.
I don't know how to explain it.
There isn't. You just have to.
Like I just put it on top of
The equation is net force equals force from the parallel plus the force from the magnet. Solve for the force from the magnet.
So like this is only,
So here's what I can tell you. The length of this vector here should equal the sum of these two vectors here.
yeah, that's what, because but I guess if I put this like that,
No, it doesn't make any difference.
I'm keeping these to study.
Okay,
because like right here is 1.2 inch and then I just put the point on top of it like that. That's
So
what
me
I
and
was-
Kaylee can
oh, because it looks like,
yeah.
no time to
that's what
study
I-
tonight for me.
But now I know.
I'm just gonna study in the morning, I guess.
okay, that's bad.
Probably easy to.
Okay, anything else?
No.
Once, twice sold?
Can we
Okay.
keep them?
If you want to hold on to them and hand them in tomorrow, you can. If you're done with them and you're feeling good about life, you can hand
Not
them
feeling.
That was a definite no. Okay.
Oh, it's okay.
Hey, you want a clear one?
Huh?
I got a clear one I stole from Mrs. Shirt. That's a horrible ruler. This one? Yeah.
What? Huh?
No, they are two separate
Do
labs.
not staple them all together.
You're gonna
Do
send it
not
into cardiac arrest. You stay
Not
together.
staple them all together.
No, he's not stressed out. You're gonna send him into cardiac arrest if you staple them together. Oh, I love it. Your hair's like long. Very long.
Longer than Morella.
At least it wasn't yellow. But you didn't like my hair.
I do. I love your hair. Your hair's so pretty.
Huh?
I love Grace's hair.
Yeah, but no, I said
like bleach.
no. I said I love yours. I said I love your hair, Gracie, but I like. I think Morella's hair is better.
Cut it out. What?
Morella's hair will always be my favorite.
I want to dye
That's
it.
typically you just made it.
Gracie, you see.
Bro, look, I want to dye my hair like the dark red, you know? I see. But then everyone's doing it now, so like.
I need to talk to Gracie.
That's a pop.
See, I wanted to make eye contact with you,
I don't like eye contact.
so you know that I still love your hair.
I believe that it should be 2/4.
We're making eye contact with Leslie.
I don't like eye contact.
You're a weirdo. Hey, be nice to Gracie. Okay?
Catherine, what box?
I can't believe I have two tests tomorrow.
No, you're
We
not.
have two?
You could have 4 tests.
Oh yeah. You have four?
You could have 4 tests.
You're right.
Really?
Growing
I
time
just
Gracie
started,
had
like,
two tests,
last week.
anatomy test, and an AP bio
When did you
all
start?
the same day. I remember that. The issue is, and she wasn't even stressed. She just
Christina will ask me, she'll be like, do you want to buy any chocolate? And I'm like, sure.
Make sure let us work on
And then
homework and
she'll be like, do you think the teacher wants to buy chocolate? I turn to the teacher, you want to buy chocolate? And she's over here like,
we'll just hide. Bro, we only got 2 more games.
are we gonna, I don't know how you find force supply.
yeah, but you're still gonna play 6 games this weekend.
It's coming in the mail or it's
Is there a schedule?
Amazon sent me like
my mom's
the
so
red stuff, the box
Don't
is
worry.
coming tonight by 10 p.m. But who knows? And then I can go get a store and get a picture board tonight.
So
Or should we use like this stuff in the library?
on this one, try
Yeah.
Oh, yeah.
you'll see that there's 2 forces
So, you
acting
want
down
to
the
go
hill. Force parallel and force friction. So your light force is going to balance out.
Yeah, I put force supply
We can ask
minus
everyone else.
force.
Anyone else wants to know?
Actually, you always talk about the sun.
See, she put it.
I guess I'm going to type in tonight as well.
You always talk about the sun. Okay.
I've been
Bro.
AP bio is my highest grade right
Oh,
now.
I never
I've been
stopped it.
97.
Okay, all right.
Yeah.
Okay.
Yeah, that's my highest grade.
We'll actually stop that for just a second.
That's so sad.
All right, so let's talk about the things that are going to be on the test. This big picture. So Isaac Newton came up with 3 laws of motion. And this is one of the very few instances where I'm going to explicitly expect you to know what each one is. So the first law is the law of inertia. All that means is that whatever velocity vector an object has, that's the one that it wants to keep. So if I've got my remote control at rest, it's going to stay at rest until I add a force to it to make it move, because Mother Nature is a lazy prima donna. Okay? Now, what's going to have more inertia? Hank the bowling ball or the little foam apple? Why?
Because he has more than that.
More stuff. Okay?
Inertia.
Now, this has less stuff, this has more stuff. So it's harder to get Hank to move. But once Hank gets moving, it's hard to get him to stop. Okay? Now, imagine that I have the apple going at 100 meters per second. And I have Hank moving at 1 meter per second. It's going 100 meters per second, Hank's moving at 1 meter per second. Which one is still going to have more inertia? Bowling ball. Why? So it has the same amount of mass. Okay? So how fast something is moving doesn't have any impact on the amount of inertia. Hank has a certain amount of inertia. I take Hank to the moon. What's going to happen to his inertia? Absolutely nothing. It's going to stay the exact same. Why?
Because mass is not affected.
Hank still has the same amount of stuff inside of him. Okay? So if I'm on the Earth and I do this horizontal motion and I go to the moon, that would feel the exact same way in terms of horizontal motion. Okay? Now, if I go to throw Hank up in the air, okay, like this, all right? So what do you know about my applied force get Hank to go up in the air relative to his downward force? Great, right? Because if it's not, okay, it's not going to go anywhere, right? So you know when something has to go up in the air, your applied force has to be bigger than the rate. You got to pay off the gravity mafia and then some. Okay. So I'm going to ask you, what's Newton's first law? Objects in motion remain in motion. Objects at rest remain at rest. But the only thing that affects inertia is mass. Now, the second law is the one that's hanging back there. Now, Newton got very verbose when he wrote this. He actually wrote, oh, the amount of force is directly proportional to the mass, and then okay, it's F equals ma. But remember, does every force cause an acceleration? No. Okay? So if Hank's sitting here, are there forces acting on Hank?
Yeah.
Yes. Is Hank accelerating?
No.
No. Okay? Now, even if I apply a horizontal force, if I apply a horizontal force to this apple, why doesn't the apple accelerate?
Your force is not large enough.
Yeah, the frictional force holding it in place is bigger than the applied force against it. So again, that's the classic situation. Just because you apply a force doesn't mean that you're going to get an acceleration. So if I give you a set of forces, like let's say a multiple choice question, okay? And I say, hey, and let's say your applied force is less than your frictional force, and I say, what's the acceleration? What's your choice going to be? Zero. Okay? So zero acceleration is very valid. Okay? Don't think, oh, Brookhamp's asking for an acceleration. No, it has to be a non-zero value. No, it doesn't have to be. Okay? The only time that's going to happen is when you have an unbalanced or net force. Now, third law. For every action there is a reaction. Okay? Do not overcomplicate this. There is no exceptions to this. It is not based upon mass. It is not based upon charge. This is a law. This is not a suggestion. This is not, well, maybe. Only if it makes sense. Only if there's a small difference in mass. Okay? There's no caveats to this. There's no footnote that says, oh, this is only true on test days. The rest of the time it's really not true. Okay? I hit the table. Do I exert a force on the table? Guess what the table do?
Normal.
So it's an equal and opposite force on me. Now, this leads to an interesting philosophical question. It's known as Isaac Newton's horse. So, according to the legend, this is back in the days of horse-drawn wagons. And this is going to be a horrible horse, but stay with me, okay?
That looks like a goat.
Back off me. Those are
That's
easy.
good.
Okay, so there's his tail, there's the mane, there's his eyes.
Oh, there's his eyes.
Okay. So, as the story goes, Isaac Newton comes up, he hooks up the horse. This is after he's published his work, the Principia. Keep in mind this is written in Latin, okay, because that was the international language of science. So he hooks up the horse. Isaac Newton needs to go in town, maybe get some fig Newtons, I don't know. And he goes to the horse, he goes, yeah, horse. So much to his surprise, the horse turns around, he goes, hey, easy there, big guy, back off me. And the horse, to his surprise, number one, can talk. Number two, the horse goes, so I've read your work, the Principia, which means the horse is really smart because it can read Latin and translate it into English, which is impressive. And he goes, just back off. And Isaac Newton's going, whoa there, Trigger, what's the problem? And Trigger goes, hey, I read your third law. I pull on the wagon. The wagon's going to pull back on me with an equal and opposite force. I'm never going to be able to move the wagon, so let's just call the whole thing off. Okay? Because your law, and again, your law, not your suggestion, not maybe, your law says that if I pull on the wagon pulls back on me with an equal and opposite force, I can't pull the wagon, unhook me so I can go eat grass. So, now if you're Isaac Newton, how do you argue with the horse? Kick it. Oh, that's good. Violence is the answer. That's a very Peter kind of answer. No,
You let it go.
you let it go.
Wow. That's a bad horse. You don't want
It's
a
a
bad,
bad
horse.
Okay. Well, let's look at it. Let's look at it in terms of your reality. Okay. Bell's going to ring in about half an hour. You're going to go push on that door, right? What's the door going to do? Push back on you with an equal and opposite force. So by that same rationale, you should never be able to open up that door.
We're stuck here forever.
We're stuck here forever. Oh my God! Okay? This is not ending well for anybody. So, but clearly, you all have opened the door. Okay? You open up the door to your car. You pull on the door pulls back on you. Right? So obviously we can make things move. Okay? You push down on the pencil, or you lift up on the pencil, gravity pulls back. So here's the deal.
How does that?
If the horse, this is a huge if the horse was standing on a frictionless surface, would the horse have a valid argument?
Yes.
Why?
Oh.
Or let's
Because,
say I put a frictionless surface in front of the door.
because there'd be no help for your force, and then the forces would be equal, and that would mean zero acceleration, right? Maybe. But then what about what about the
Hold on.
opposite force for friction? That
Okay,
doesn't
so
make.
here's the deal.
He's lying.
So look at it this way. Mason, you've pushed a blocking sled, I'm guessing, at some point in your life. Okay? Not the best job in the world. Okay? So imagine you go to Coach Guzman and he goes, "Hey Mason, I need you to push on the blocking sled." You go, "Hey Coach, I'm taking physics. I always start." Mr. Burkamp taught us to push, if we push on the blocking sled's just going to push back on us, and we can't move the blocking sled. Okay, Guzman is number one, he's going to hunt me down. Okay, he's not going to end well. And he's just going to say, "Shut up and push the block." So, why do you wear cleats on your shoes?
Increases in friction.
Okay, so when Mason goes to push on the ground, okay, what does the ground do? Ground pushes back with an equal and opposite force, right? When you go to push on the door admittedly pushes back on you with an equal and opposite force. But you're also pushing on the ground, and the ground pushes back on you with an equal and opposite force. So as long as that set of equal and opposite forces between your shoes and the ground is greater than the equal and opposite forces between you and the door, you can open up the door. You can drag, the horse can make the wagon move. Mason can push the blocking sled, okay? Maggie's going to hit a volleyball, okay? She's going to hit the volleyball. What's the volleyball going to do? Hit her back with an equal and opposite force, right? Now, conveniently, when Maggie does that, but which accelerates more, the volleyball or you? Volleyball. Hopefully the volleyball accelerates more than you do. Sometimes, okay, sometimes. So, the horse has a valid argument, okay? When the horse does pull on the wagon does pull back with an equal and opposite force. That's valid. But that isn't the only isolated set of forces that exist, okay? There's another set of forces that exist between his shoes and the ground. Okay.
See, when you said the horse on a frictionless surface, I immediately thought of a horse on just an ice rink.
Yeah, that's basically it. Horses on ice. That's nice. Okay. 4 fundamental forces. What are the 2 that impact your lives most? Gravity and friction.
Normal.
But which fundamental force creates friction? Oh, it's not going to end well tomorrow.
Electron.
I see pain and suffering in my future.
Chihuahuas.
Where's normal?
We said that.
Electrostatic. Okay? Or electromagnetic, depending upon
Yeah.
which one it is.
We
Okay?
said that.
Yes, if you have not looked at the lecture notes that I've given you, read those. That's why I gave them to you.
Wait,
Okay?
let me look right now.
Eli, you're the one that said you never read.
So, the electromagnetic force is the most diverse. It's what allows you, if you're cold outside and you rub your hands together, that's the electromagnetic force. That's what holds your cells together. That's what allows us to have light. That's what creates friction. That's what creates the normal force. That's what creates you from being pulled to the center of the earth by gravity. Okay? So it allows us to make toast. All right? Is any number of things. So it is the broadest and most diverse. It does create friction. So friction is the manifestation of the electromagnetic force. And you need two things to create the electromagnetic force. You need two charged particles, okay, positive and negative. That's going to be an attractive force. Or if they're both positive or both negative, they repel. Okay? It also allows you to create light. So for example, first block, I was teaching my Chem 1 students, bless their little hearts, about what's necessary to emit light. Okay, electrons have to jump energy levels, and they come back down and they give off photons, right? So that's the most diverse, okay? Without the electromagnetic force, we would not be here having this discussion because we could not form any kind of molecules because they would not be held together, okay? What are the two forces that exist within the nucleus? Strong nuclear and the, which of those four forces am I not going to ask you about? Weak nuclear. I'm going to tell you straight up right now. These are going to be multiple choice questions when I ask you about these. I'm going to give you all four forces, A, B, C, D. Okay? Strong, weak, gravity, electromagnetic. Which one do you not pick? Weak nuclear. So help me, if any of you pick the weak nuclear force, I'm going to flunk you. Okay? What's the strongest of the four forces? Strong nuclear. I promise you I'm going to ask you that question. Okay? And I'm going to say I'm going to flunk you if you miss this question. Okay?
Strongest of all forces.
Yes. I will flunk you if you miss that question. It is a gift. Accept it. Do not overthink it. Go, well, Brookhamp's trying to trick us. No, I'm not. Okay? I'm not. Okay. What other kind of problems do you think are going to be on the test?
Probably some long answer ones.
Well,
Do we have to graph? Do we have to
maybe
make
some
a
calculating forces.
free body
Oh,
diagram?
maybe a rocket.
Nah.
Maybe a rocket.
Oh, I did a horrible one on this.
Okay? So let's say that I give you the force of the rocket is, I don't know, 100 newtons. And the mass of the rocket is, I don't know, 5.04 or 5.0 kilograms. Okay? 100 Newton rocket, or the force of the inches is 100 Newton. The mass of the rocket is 5 kilograms, and I'm going to ask you to calculate the acceleration. This problem is going to be at the bottom of the front page. I will even tell you exactly where this problem is going to be. It's at the bottom of the front page. It will actually involve the Starship Enterprise. Okay? Starship Enterprise. Don't worry about it. 100 Newton force, it's mass of 5 kilograms. What are you going to do wrong?
You're gonna put that as F net.
Yeah, you're going to set the 100 newtons
Yeah.
as your net force. You're going to take 100 newtons and you're going to divide it by 5, and you're going to get an acceleration of 20 meters per second squared. You're going to go, physics is easy. I don't know what Brookhamp's raving about. Okay? Who did you not pay off?
Gravity.
Gravity Mafia. You always have to pay off the Gravity Mafia. Okay? I'm going to say, draw a free body diagram. And you better realize, gravity is acting downward. So how are you going to find the value of that gravitational force?
Mass times the acceleration.
Yeah, you're going to take 5 times 9.8 meters per second squared. You're going to get 49 newtons. Trust me on that one. So I got a negative 49 newtons. So I got a 100 Newton force going up. So Topher paid the freshman $49 for the watch. He sold it for $100. What's his net profit? 51. When in doubt, make a chart. Says, force applied, force opposing, force net. I have an applied force of 100 newtons. I have an opposing force of negative 49. I have a net force of 51. Okay? So the more ways you can think through these problems, the better off you're going to be. What's the only time you don't have to pay off the gravity mafia?
In deep space.
Yes. And
Or
there's going to be a
vacuum.
problem like that. That's going to be on page 2. I can tell you where it's going to be. It's going to be on page 2. I'm going to say the effects of gravity can be reasonably ignored. You are in deep, 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 deep space. Okay? Deep space. And you apply 100 Newton force. Then what's your acceleration going to be? With this same setup. Then it would be the 20 meters per second squared because there's no gravity mafia to pay off. So you always pay the gravity mafia, okay? If you're not sure, you all did an assignment on net forces, okay? You did this. You had an assignment on net forces. There is going to be so much of that test is going to come over this concept of net forces. You're going to have a rocket problem. I promise you, you're going to have a rocket problem, maybe even 2, okay? Heavy on the rockets. I like rockets, okay? What else do you think is going to be on the test?
What we just did.
Huh?
What we just did.
Yeah, inclined planes, magnets. So grab that, let's go to the back.
Oh, that Atwood thing too.
Oh, that's gonna be there too. So break the camera. Hooked over the end of the table, like this, okay? Is it going to accelerate when I let go of it? Clearly it's
Yes,
going to
sir.
accelerate, right? So, how are you going to calculate the value of the force that's making it move?
Distance. Oh, the force? My
Yes.
bad. Sorry. I was going to use acceleration.
I got a 20 gram
Yeah,
mass
that.
on the
You
end.
just do the gravity times that.
Say 20 grams, how many kilograms is, how are you going to get from grams to kilograms? Divide by 1,000, which is going to be 0.02. So I'm going to take 0.02 times 9.8 meters per second squared, you're going to get 0.196. So I have a 0.196 Newton force acting to make everything move, right? That's it, okay? Is gravity pulling down on this, on the cart? Yes, but normal force balancing out. So as long as there is no friction, this is the only game in town, okay? If you look at force applied plus force opposing equals force net. As long as I tell you that there is no friction, this is it. There is nothing else happening. This is the only game in town. Now, to calculate a theoretical acceleration, this is 0.196 newtons. That's your net force. What are you going to divide by to get the mass? The 20 grams, the mass of the cart, or the combined mass?
Combined mass.
You always, always, always divide by the combined mass. Okay? Always. Your last step to get an acceleration is that you always divide by the combined mass. So I'm going to let go of this. Oddly enough, it begins to accelerate. Okay? Now, I'm going to take this off. Now let's not worry about that. Now, I'm going to put this underneath the front edge. And now I'm going to let go of it. So now what's going to happen? Goes the other way. Okay? So if I let go of this, and it's a frictionless inclined plane, what's the only force in town? Gravity. Well, what component of gravity? Force parallel, right? So how are you going to calculate force parallel? FG sine theta. Okay? So I let go of this. Since it accelerates, I know there has to be an imbalanced force, right? So in this situation, if there's no friction, I could take, it's the same idea. I would take my force parallel, divide it by the mass, there's my theoretical acceleration. Now, what if there's a little bit of friction? Okay, so imagine me holding on this string is creating some friction as it falls. So which direction is the frictional force acting?
Up.
Up the hill. Which direction is my force parallel acting?
Down.
Now, as soon as I let go of it, and it begins to accelerate down the hill, which force is bigger?
The parallel.
Parallel is bigger than my frictional force. Now, what if it accelerates up the hill? My applied force is bigger than my friction, or whatever force is acting down the hill. Now, let's combine them. Oh, evil girl. Yes, I am. So now I'm going to put this 20-gram mass on the end of the string. Okay? I'm going to have it like this. Okay? And then I'm going to let go of it. So what's bigger? My force parallel acting down, or my applied force from the end of the string? Force parallel. So how would you calculate the net force? So I've got a force parallel going down the hill. I've got the weight of this as in
Ooh, you
upward
can
force.
find
So this is
acceleration.
0.196 newtons.
Yeah.
Okay? So since this is 0.196 newtons, and I let go of it, what does my force parallel have to be bigger than? 0.196 newtons. It might be 0.3, something like that. So let's just round this. Let's make the math easy. Let's say this is 0.2. If this is 0.2 newtons, and let's say my downward force is negative 0.3, what's my net force going to be? Negative 0.1. Okay? Now, let's say I swap out the 20, and I put a 50-gram mass on the end of the string. What have I done to my force parallel? Nothing. Okay? But now when I let go of it, now it begins to accelerate up the hill. Now which one is bigger?
Force applied.
My applied is bigger than my
Force
parallel.
parallel.
Maybe this is 0.4. Maybe that's negative 0.3. My net force is now 0.1.
For your force parallel on that one, would you still, like, to find it, would you use the whole entire mass?
No, it's just this.
the
It's
car.
just this. It is just this.
Okay, that's what
The
I
only
thought.
time you
but-
divide by the total mass is when you're finding the acceleration.
Okay.
That force parallel is only based upon this. Now, let's put it all together. So now I'm going to put the magnet in here. So you mark my words, you're going to have a problem like this on the test. You mark my words, okay? And it's going to look just like this. I'm going to have a weight on the end of the string. I'm going to have a cart. I'm going to have a magnet. This is what this diagram is going to look like, okay? Now, I'm going to let go of this. Now, what are the forces? I let go of this, right? What are the forces acting on the system?
Force applied.
So I got my force applied going that way.
The
I've got my force parallel acting down. What's the force from the magnet? Opposite of motion. So, now, look what happened. If I don't have the magnet, I get a certain acceleration. If I have the magnet, I get a smaller acceleration. So which direction is the force from the magnet always going to act? Opposite. So that's the first thing you do when you get this problem. Ask yourself, it's either going to accelerate up the hill or it's going to accelerate down the hill. So if that thing accelerates up the hill, you know that the forces acting up the hill have to be bigger than the forces acting down the hill. Okay? Now, if I let go of this and it begins to accelerate down the hill, if it accelerates down the hill, which direction is the force from the magnet going to act? Up the hill. Okay? And I will explicitly tell you, and I am going to give you the force from the magnet. I'm going to give you that numeric value. You just have to know what to do with it. Okay? So, if the cart accelerates down the hill, the force acts up the hill. If it accelerates up the hill, from the force from the magnet acts down the hill. Got it? Good? Great. Now, you're going to have a problem like this. You're also going to have a situation, while we're here, that I'm going to have like an Atwood machine. So I'm going to have a 50-gram mass on one side, and let's say a 20-gram mass on the other. Okay? So we're going to have a setup like this. 50-gram on one side and a 20-gram mass on the other. Which direction is it going to accelerate? Towards the 50 or towards the 20? Okay, so it's going to go like this, doink, like that. So, with an Atwood machine, gravity storm. So imagine that, here's the boy, okay? I got a 50 gram, I got a 20 gram. Which do we call the applied force? The bigger, the weight of the bigger one, or the weight of the smaller one?
Bigger.
We're going to call this the applied force. The weight of the smaller one is going to be the opposing force, right? So you got this, it's going to go like this. So let's say, to make the math easy, let's say this weighs 1 Newton. Let's say this weighs 0.8 newtons. This one weighs 1, this one weighs 0.8. What's going to be my net force? 0.2. That's going to be the difference between those two. Then how are you going to get your acceleration? Divide by the
Total
combined
mass.
mass. Got it? Promise you. There's going to be
Yes,
something,
sir.
I promise you. Okay,
Yes,
back we go.
Yes, sir. Yes, sir. Yes, sir. Nice. Nice.
Oh, see, look, it came in handy.
Okay, are we still going? No.
Yes.
Okay. This is going to be the last problem on the test. I'm going to tell you exactly what it's going to be. So it'll be the last problem on the last page. Okay? I'm going to have a mass, say 0.2 kilograms, hooked up to a 0.4 kilogram mass. This is exactly how it's going to play out. The first one is going to be completely frictionless. No inclined planes, no magnets, no nothing. How are you going to find the force acting on the system?
Force of gravity times the 0.2 kilogram.
Right. You're going to take 0.2 times 9.8 meters per second squared, and you're going to get 1.96 newtons. Okay? Whatever the mass is suspended from the end of the string, because that's the only force in town to make it move. That's your force, right? If it's frictionless, how are you going to get your acceleration? What are you going to divide by? Total mass of 0.6. So you can take the mass of whatever's hanging from the string, take that times 9.8, divide by the total mass. That's all you have to do. It's going to be the easiest problem on the test. That m times g divided by the total mass. And yes, there's problems like this on the review. The next thing I want to do is I want to introduce friction. Okay? Now, if I tell you the coefficient of friction, say, is, let's say, mu equals 0.2. Remember, friction only occurs between that surface and the table. The mass on the end of the string has nothing to do with the calculation of friction. It's not part of the story. Okay? All that's doing is making it move. So when you calculate the frictional force, only use the mass that's up there on the end of the table. Okay? That mass has nothing to do with the frictional force. Now, is your acceleration going to be bigger or smaller once you introduce friction? Smaller. Why?
Friction's acting opposite.
Yeah. Now you have an opposing force. So you know your acceleration once you introduce friction has to be less than the one without friction. Okay? Otherwise, it's like, that's weird, there's friction, but you accelerated faster. Really, that's kind of cool. Okay? No. Okay, so those are going to be the big problems that are going to be on the test. I'm going to give you the review. There's going to be Atwood machines, there's going to be a problem like this, there's going to be rocket problems. Okay? And then you're going to get the answer key to the review. If there's aspects of this, when you're getting ready to study, you're like, oh man, I'm not digging this Atwood machine. Okay, we did an entire lab on them. Okay? Find the questions on the review. Find the part that you feel least confident in. That's what you focus on the most. And then you work those problems, and then you change the numbers, and you work the problems again. And then you create a group chat that says, hey, somebody make up an Atwood machine problem. Somebody make up an inclined plane problem. Write your own test. Okay? It's like, seriously, y'all have been students long enough. Write your own test. Like, how would I ask that question? Huh? You know what's one multiple choice question going to be?
2 points.
No.
What's the strongest force?
What is one multiple choice question I'm going to ask you? What is the strongest force?
Strong
I
nuclear
promise you, I'm going to ask you that question. I promise. on the sheet. Okay, so let me hand that stuff out. Leslie, if you wanna go, you can.